Okay, so this beam, we have some forces in different directions and a torque about the long axis. And it says to calculate the internal loads and then calculate the elongation due to internal tension compression. Why don't I skip the internal loads? We've done a lot of that, unless you have a specific question about that. But let me just go on to part B. So one key thing that you have to recognize here is that you can, because of the superposition principle, we're doing all of these calculations independent of each other. Okay, so we can do this problem as if there was no 4,000 Newton meter torque and no 3,000 Newton upward force, and just deal with the elongation stuff if all we want to calculate is the elongation. Are you with me on that? Okay, so I'm going to just go straight into, so I'm only going to do horizontal stuff. So I'm going to forget about everything else. I don't care about that stuff. I only want to calculate the internal tensions. So we have a 4,000 here, an 8,000 here, a reaction here. That's all the horizontal forces. So Newton's second law in the x direction says positive R plus 4,000 plus 8,000, everything's pointing to the right, so they're all positive, is equal to 0. And so R is equal to negative 12,000. And so now I'm going to go to the cuts. And I need to do this because the internal tension is going to be one thing for the first half, and it's going to be something else for the second half. And so cut 1 is relevant for x values. What, the length is 2. Oh, well, okay. I didn't notice the weight acting, but again, the weight is vertical. So we can do the horizontal calculations without worrying about that. So that actually doesn't change anything, even though I didn't notice it. So we're going to go from x's from 0 to 1. And bless you. A free body diagram looks like this. There's a 12,000 pointing to the left. We haven't gotten to the 4,000 yet. And then there's an internal tension here. And so Newton's second law says negative 12,000 plus T is equal to 0. So T is equal to 12,000. And so this is what we're going to use for that first half in the elongation calculation. And now we'll go to cut 2. So the free body diagram here has a 12,000 this way. This time we've made it past the 4,000 Newton force. And then we have the internal tension. So Newton's second law says negative 12,000 plus 4,000 plus T is equal to 0. So T is equal to 8,000. And now we can do the elongation calculation. We're given the stiffness. We're not given the area. You know, we're going to use this formula for the elongation. It's equal to the sum of the parts. In this case, there's only 2 pieces, so I from 1 to 2 of the tension on that piece times the length of that piece divided by the Young's modulus, which stays the same through the whole thing, times the area that stays the same for the whole thing. To calculate that area, it says this is a rectangular cross section, 0.1 times 0.05. And so that is 0.005. And so delta is equal to, so for the first piece, we have 12,000. The length up to that 4,000 Newton force is 1 meter. E is 210 times 10 to the 9. A is 0.005. And then the second piece, we have 8,000. The second half also has a length of 1 meter. The Young's modulus is 210 times 10 to the 9. 0.005. And if I plug all this in, I got 1.905 times 10 to the minus 5 meters. And it's positive, so that means that the length increases by that amount, which makes sense because the whole thing is in tension. Okay. What if the cross-sectional area was smaller? Would that number go up or down? It would go up, yes. The smaller amount of material would have a harder time resisting that stretching, and so it would go up. What if the Young's modulus went up? Would, if we had a stiffer material, would that go up or down? It would go down. The stiffer material resists that stretching.
Is it e to the 5 or e to the
-5. Yeah, e to the 5. That's what 190,000 meters. That's a large deformation. Okay.
So the vertical forces don't affect it at all.
That's right. Because of the superposition principle, everything going on is small. The deformations are small, and the stress-strain relationship is linear, and that allows us to do the calculations independently and then just add them at the end. Okay. So 1 times 10 to the minus third is 1 millimeter. So this is, 1.9% of a millimeter. And now we're going to, which number was it again, Marco? Second. Statically indeterminate systems, number 2. Okay, so we have this iron bar that has 2 different cross sections, and then there's a force applied a quarter of the way down from the top, and it gives us the 2 cross-sectional areas. Oh, and then there's a gigantic temperature increase. So presumably this is a calculation for inside some kind of engine. And so we are going to start by doing the statics. Remember, you always start with the statics. They just won't give you enough equations to solve by yourself. So free body diagram of this. We have a force down of 50,000 here. And then we have a force. I'm not going to make any guesses about the directions of the forces. I'm just going to call this RA in the positive direction and RB in the positive direction. And Newton's second law says RA plus RB minus 50,000 is equal to 0. So RA plus RB is equal to 50,000. There is our one useful equation. I mean, you could do the horizontal Newton's second law equation and you could do the moment equation, but they would both just give you 0 equals 0. So this is the only useful one. So I'm going to just set this aside for later. This is my first star equation. And so we're going to need a geometric constraint, a geometric restriction on what's happening. Okay, so now I'm going to calculate the total elongation. And once I calculate the total elongation, I'm going to have it as a function of one or more of these variables. Okay, and so once I get my expression for the elongation, how am I going to use that expression to give me another equation in my system?
Internal stresses?
Well, we will calculate the internal loads, and then we'll use those to calculate the elongation. Yep.
Can you set the elongation to 0?
Then we'll set the elongation equal to 0 because with the fixed top and bottom, that length doesn't have anywhere to go. So that the reaction loads are going to be whatever they need to be to basically counteract the elongation that comes otherwise. Okay, so I'm going to first calculate my my internal tension. So I'll do my cut 1, and just because I'm used to it, I'm going to draw it horizontally here. But you have to make sure that the directions of your things make sense. So this is my RA. We haven't gotten to the 50,000 Newton force. And then we have our internal tension here. This is for X values from 0 to, it's 1 meter long. It's divided into half, so 0.5 meters. The force is 0.25, but the oh yeah, you're right. This should be so I have it tipped over from the way it is to the right. So I should be going up to that force, which should be 0.75. And then Newton's second law says RA plus T is equal to 0. So T for this part is equal to negative RA. Is what?
Change.
Should it change from what?
It will add like the small rectangle since we moved up.
Yes, you're right. It could. You're right. It it has to represent everything from this to this to this. But since the cross-sectional area doesn't come into it, this free body diagram works perfectly well no matter which of these cases I'm dealing with. Okay? Yeah. So here's my internal tension for the first cut, and then my second cut is going to be for x's from 0.75 to 1. And so this one, it's definitely going to include some of this, but not all of it. And we're going to get to the 50,000 Newton force. We have the RA here. And then the only other thing is the internal tension. And so Newton's second law says RA minus 50,000 plus T is equal to 0. And so T for this piece is 50,000 minus RA. Okay, and now I have to calculate the elongation for this thing. But notice that, so I'm going to have to, for the elongations, I'm going to have to break this up into 3 chunks because the chunk from the floor to here has one cross-sectional area. The chunk and one tension. The chunk from here to here still has the same tension, but it has a different cross-sectional area. So anytime any of those variables change, you have to use another part of the sum. And then the last one will be from here to here, and that will have its own tension, but the same cross-sectional area as this one. And this is an iron bar. I don't remember what E is for iron. I guess it doesn't matter. Well, it'll matter for the temperature increase. So,
it was like 139 for Young's modulus.
okay. 130 times 10 to the 9. Okay, let's use that. So now for the elongation, the first piece, the piece from the floor to the change in area, is the internal tension. So that's negative RA times the length, which is 0.5, divided by E, which is 130 times 10 to the 9, divided by the cross-sectional area, and that is 0.05. And now we'll add that to the piece that goes from the shoulder, where the area changes, to where that 50,000 Newton force is applied. We still have the same internal tension of RA. The length this time is only 0.25. The Young's modulus is 130 times 10 to the 9. And the cross-sectional area is only 0.01. And then we'll add on the last piece. This one has an internal tension of 50,000 minus RA, a length of 0.25, a Young's modulus of 130 times 10 to the 9, a cross-sectional area of 0.01. Everybody see what's going on with that. And then we're going to set that equal to 0.
Right, so whenever you do this, if you add up all the lengths, you should get the length of your body.
That's true. Yes.
So
Correct.
I just need a way to like double check to make sure.
Yep, that's exactly right. And so I guess I'll multiply both sides by the denominators, and I get rid of these. And then I have, so negative RA plus, what's a quarter of 50,000? 12,500? Yes.
You told me to do that if all the are the same.
Yes.
So like,
Oh, yes.
5
You're right. I'm sorry. That's my second screw up. I won't make any more. Stupid. Okay, so we can, so we can't divide those. Yes. But we can divide the 130 times 10 to the 9. So, and so I can write this as what? Negative 10 RA minus 25 RA minus 25 RA plus 5 times 10 to the 6. And we get 60 RA is equal to 5 times 10 to the 6. And so RA is equal to 83,333. That is not right. Yep. Yes, that's right. So by 0.25. So that's 12,500. 125. 12,100. So I think that should be 1 point 1, no, 1.25 times 10 to the 6. Is that right? Maybe.
That's what I.
Okay. So now we'll divide. That doesn't count as a screw up though, because that was just arithmetic.
Okay.
1.25 times 10 to the 6 divided by 60. So 20,833. And then we can go back up to the star equation. And RB is 50,000 minus that. So that is, I'm not doing any other stuff in my head for the rest of the day. Uh, 29,167. Okay, so okay, so those two forces both counteract. and the area and the proximity to the force, sort of work together to come up with the ratios there. And then now we have to take into account this huge temperature increase. We have to do some other stuff. So what's the stress tensor for a point in the bottom half? Okay, so this is our first time doing a problem where we take this statically indeterminate system and we use it to calculate stresses. But it really isn't anything too different from what we've done before. It just took us longer to come up with those external loads. So now you can say in the bottom, stress tensor for a point in the bottom half. So in the bottom half, the internal tension is negative RA. And so that's equal to negative 20,833. I just used the tension expression that I had before and plugged in the value that I had for RA. And so now, due to tension and compression, the XX stress, or the normal stress along the long axis of this bar, is just T over A, which is negative 20,833 divided by 0.05. So that is 4.16 repeating times 10 to the fifth. And so the stress tensor has this in the XX position, 0 everywhere else. Any questions about that stress tensor? So now we're supposed to calculate the strain. So we're just going to take, the Voigt strain is just going to be the compliance matrix for iron, which is 130 times 10 to the 9 for E. And then I don't know what Poisson's ratio is, but let's say it's
I think it's at 0.25.
0.25. Okay, and then we'll multiply that by the Voigt stress. So 4.16 repeating times 10 to the fifth, and then zeros everywhere else. And what elements of the strain are going to be non-zero?
The normal.
Yeah, very good. The normal. And I left off the negative sign here. That's also not a screw up. That's just a negative sign. That's a totally normal thing. So, okay, so this should be negative. This should be negative. So this should be negative. And so what are going to be the signs of the normal strains when we do this calculation? What's going to be the sign of the X normal strain? Any other guesses?
Negative.
Negative. Very good. And then what are the signs going to be of the Y and Z normal stresses? Those are going to be positive. Yes.
What's the reason for that? Or just-
because that is the Poisson's effect that's making those other two, those off-axis strains happen. So that's the, like in Bugs Bunny, if you whack something with a hammer, it gets fatter.
Okay.
And if you stretch it by its neck, it gets skinnier. That's the Poisson's effect. Um, so now we have to do the same thing, but we have a temperature increase of 280 degrees. So
No me queda put another bottom, like the top hole.
the like start at the statics again.
No, I mean, where would you make the stress tensor for the bottom half?
Oh yeah, we did it for the bottom. Did it say the top too?
Oh, just the bottom.
It only said the bottom. So, but yes, we could do it for the top half, and we would get something. And we couldn't just do it for the top half, by the way. We could do it for the top quarter or the next quarter down because those internal tensions change. But yeah, we could do it at any of those points. All right, so now we're going to do it incorporating the change in temperature, and the statics and the cuts stay the same. There's nothing that would change any of those things. So what we have is that delta due to internal tension and compression is equal to, we have all this stuff, negative RA times 0.5 divided by 130 times 10 to the 9 times 0.05. And then plus negative RA times the length of 0.25, yep, divided by 130 times 10 to the 9. This time the cross-sectional area is 0.01. And then plus the internal tension for the last piece is 50,000 minus RA. The length is 0.25 divided by 130 times 10 to the 9 times the cross-sectional area. And we can't set this equal to 0 yet because we have another source of elongation with the temperature increase. And that's that thermal expansion that's going to come from raising the temperature. So now we're going to calculate the thermal effect, the thermal expansion. Did you happen to look up a coefficient of thermal expansion for iron?
11.8 e to the negative 6, 1 over Celsius.
Great, thank you. They seem to all stay in the ballpark of 1 times 10 to the minus 5 for metals.
If the coefficient is smaller, it has a greater degree, that means it deforms less with heat.
Okay, so the equation for it tells you all that. So the thermal expansion is equal to the coefficient times the length times the change in temperature. So the bigger that alpha is, the more it expands for the same temperature change. Okay. So Pyrex glass, remember the Pyrex glass example has a small coefficient of thermal expansion. Okay, so this is equal to 11.8 times 10 to the minus 6 times the length. And the thermal expansion part is nice. You don't have to break it up into individual pieces. The whole thing behaves the same unless the temperature is different for the different parts. So this is a length of 1 and a change in temperature of, since it's going up, the delta T is positive 280. And so this is going to be a huge thermal expansion. So 0.033. So 3.3 centimeters. And now we're going to come up with this expression for the total change in length. So that is going to be negative RA times 0.5 over 130 times 10 to the 9 times 0.05 plus negative RA times 0.25 times 10 to the 9 times 0.01, and then plus the quantity 50,000 minus RA times 0.25 divided by 130 times 10 to the 9 times 0.01. And then last, we'll add on our elongation that came from raising this temperature and set that equal to 0 because the floor and ceiling don't let it expand or contract. And so I can write this as 0.033 is equal to so this is 7.692 times 10 to the minus 11 times RA. I'm just combining all those numbers. Plus 1.923 times 10 to the minus 10 times RA. And then we have 1.923 times 10 to the minus 10 times the quantity RA minus 50,000. Yeah. I moved that, all of the ones with variables to the other side of the equation. Okay, so 50,000 times this guy plus 0.033. Okay, so now we have 0.03301 is equal to, all I did was distribute this number through the 50,000 and get that over on the other side. And this is all equal to 4.6155 RA. I left off a very important factor of 10 to the minus 10 RA. And so RA is equal to 7.152 times 10 to the 7. And now we have, from our statics equation way up here, we have that those two have to add up to 50,000. So 7.152 times 10 to the 7 plus RB is equal to 50,000. So RB is equal to negative 7.147 times 10 to the 7 pascals. And so if you draw this now, what? You're right, it's in newtons. That's not a screw up either, that's just units. So we have the 50,000 here. We have RA in the positive direction. And then RB is now in the negative direction, 7.147 times 10 to the 7 newtons. Okay, so before we increase the temperature a huge amount, both of those two forces were counteracting the 50,000 Newton force. Does it make sense that now they're pushing against each other? Well, think about the fact that the main thing that's going on, the overwhelming thing that's going on, is that this metal is just expanding. And so if this metal expands, the floor and ceiling are going to have to push really hard to not have it break through, you know? And so those just have to apply a huge compressive force at both ends to maintain this constraint. And then what about the stress tensor? Well, we still have these same internal loads. So T is equal to minus RA. For the part that we're interested in here. So T is equal to negative 7.152 times 10 to the 7. And so the XX normal stress is T over A, which is negative 7.152 times 10 to the 7, divided by the cross-sectional area, 0.05. And so that is 1.4304 times 10 to the 9. That's more stress than iron can withstand. Negative, thank you. And so the stress tensor is negative 1.4304, and then zeros everywhere in gigapascals. And basically, if you're using an old-fashioned material and expressing your answer in gigapascals, you've already lost this fight.
I like the advanced steels and composites.
Yes, apparently. Were we looking that up together?
Yeah.
Yeah. So apparently there are some very high-tech materials that can, in the right situation, can withstand stresses that big, but not old-fashioned ones. Okay. So now that's okay. We've spent a lot of time, but what we're doing today won't take very long. The stuff that we have to get through. So today we're going to talk about, and we have a quiz today. So we have 20 minutes. Maybe that's too much to ask, but we'll see. So we're going to talk about displacements due to torque, and we're going to think about the angle of twist. So angle of twist due to torsion. And so we're first going to talk about the angle of twist. And then we're going to use that in statically indeterminate systems. Just the same approach that we used for internal tension and for thermal expansion. But of all of them, this is probably the easiest one. Okay, so I'm going to try to draw this. So if you have a member like this, and you apply equal and opposite couples to both ends. So you have a T going that way, and at this end you have a T going the other way. And let's say that before the deformation, you drew, painted these lines on this member, okay? Then if you hold the left end still and let the right end deform, think about the right-hand rule for a second and get your bearings on which way this is going to rotate. The right end of this, since this torque is this way, so your fingers are rotating this way, that line after the deformation is going to be down here somewhere. Okay. And so the angle of twist that we're talking about is this. And notice that on the other end, this would gradually close until it met that point there. And I'm going to denote this phi. And so that's the angle of twist that we're talking about.
Or is that like not theta?
Theta is this guy, phi is this guy. They're like the two Hall of Fame members of angle representation. And the angle of twist is the sum. And again, you're just going to do it in pieces and calculate the internal torque and then do it in pieces. So this is a sum from 1 to however many pieces you need of the internal torque of that piece times the length of that piece divided by G for that piece. I'll tell you what that is. Divided by the polar moment of inertia for that piece. So that's the formula. And G is E over 2 times the quantity 1 plus nu. Does anyone recognize, does that look familiar? E over the quantity 2 times 1 plus nu. Where have you seen something like that? Yeah, so that is the reciprocal of the shear terms in the compliance matrix. So basically, and I just say the the reciprocal of the ones in the compliance matrix because we don't, in this class, use the stiffness matrix very often, but those are actually the terms in the stiffness matrix for the shears. So you can think of this as like a shear stiffness. So given that that's a shear stiffness, look at this formula and notice how similar it is to the elongation for internal tension. If you notice this similarity, then you only have to remember one of them and you automatically remember the other one. We have the load times the length of the piece divided by the stiffness of the piece times the geometric resistance to the deformation. So when you're trying to stretch something, what resists that stretching is the cross-sectional area. Okay? When you're trying to twist something, what resists that twisting is the polar moment of inertia. But that's a totally geometric thing. If you have silly putty and steel, both with the same cross section, they have the same polar moment of inertia. What's different between them is that shear stiffness. Okay. Okay, so let's do an example. Let's say we have a cantilever bar. And at the midpoint, we have a torque of 200 Newton meters. And then at this end, let's say we have a torque going the other way of 50 Newton meters. And let's say G for our material is 80 times 10 to the 9 pascals. And the polar moment of inertia. So I didn't tell you what the radius is of this bar. But instead, just as good for this application, I just gave the polar moment of inertia. So this is 1.57 times 10 to the minus 8. Does the polar moment of inertia go up or down when the radius goes up?
It should go up.
The polar moment of inertia goes up. Yes. The bigger the radius is, the more resistance there is to it twisting. Yep. You can also, bless you, you can also think of the formula for the polar moment of inertia, which is just pi over 2 times radius to the 4th. We saw that with stress due to torque. Okay, so we got this thing. The whole thing is 1 meter long. And we want to calculate the angle of twist for the whole length. Okay, well, the first thing we have to do is figure out what those internal torques are. So we have a reaction torque here. I'll call that fancy TR. We have a torque here of 200. A torque here of 50. And now we can use the moment equation about the x-axis. These calculations are easy because everything's couples. You don't need about points or anything. So we have fancy TR plus 200 minus 50 is equal to 0. So TR is equal to negative 150. And now we can do the cuts. So for x from 0 to 0.5, we have a torque going this way of 150. We haven't gotten to the 200 yet, so the only other one is the internal torque. And so the moment equation says negative 150 plus t is equal to 0. So t is equal to positive 150. And then we'll do the second cut. This is for x's from 0.5 to 1. So there's the 150. This time we're past the 200, so we have a 200 here. An internal torque. The moment equation says minus 150 plus 200 plus t is equal to 0. So the internal torque on this half is negative 50. All right, so now we have the internal torques for the two parts, and now all that's left is calculating the angle of twist. So this is going to be, so we have the first half that has 150 times the length divided by, was this 80 times 10 to the 9? And then 1.57 times 10 to the minus 8. Is that right? And then we're adding that to negative 50 times 0.5 divided by 80 times 10 to the 9 times 1.57 times 10 to the minus 8. And we get 0.0, it's really 0.040. And what are the units on this? Everybody's checked out because I went so long without any screw ups. What do you think what do you think the units are? Radians. Very good. And how could you figure out without looking it up in a book what the units are there?
So angle.
Well, it is an angle because there's no units exactly. That's what I was getting at. If you go to that formula, put units in of Newton meters, meters for this. G has units of pascals, which is newtons per meter squared. This has units of meters to the fourth. Well, to do this, you'd have to remember what all the units of those things are. But if you put them all together, you get a unitless thing, which is radians. Okay, degrees are not unitless. That's degrees is its own kind of unit. Okay, yes.
The length for the -50, why is it 0.5?
The whole length was 1 meter, and that was supposed to be acting right in the middle. Okay, I'm going to squeeze one of these in. Okay, so now we're going to statically indeterminate systems. It's so simple. You can get it from one problem. It's going to be the exact same approach as it was before. We're going to do the statics, get an equation from the statics, but it won't be solvable. That's what statically indeterminate means. And then we'll use restrictions on the motion to come up with another equation. So let's say that we have two walls and a bar in between them. And let's say that a third of the way along the bar, we have a torque of 50 Newton meters. And I'll give dimensions. So let's say this is 0.5 meters, and this is 1 meter. So the whole thing is 1.5 meters. So first, we'll do the statics. A free body diagram looks like this. You have an unknown torque over here. I'll call that fancy TA. Unknown torque over here, that's fancy TB. And then here you have this torque of 50. And so rotational Newton's second law says TA plus TB minus 50 is equal to 0. So my first start equation says TA plus TB is equal to 50. Okay, now we have to do the cuts because we have to calculate the internal torques. So cut 1 is for x from 0 to 0.5. So here we have TA, and then the internal torque, T. So the moment equation says TA plus T is equal to 0, or in other words, the internal torque is negative TA. And then the second cut is from 0.5 to 1.5. So we have the TA, and we have the torque going the other way of 50, and then we have the internal torque. And so the moment equation says TA minus 50 plus T is equal to 0. And so T is equal to 50 minus TA. I'm sorry I'm rushing so much, but the process is so similar to what we did with internal tensions. And now that we have this, we can say that the angle of twist, the total angle of twist, is the internal torque on the first piece times its length divided by, I'll write this as GIP. I didn't even give you those, but they're going to cancel out. Plus the second piece is the quantity 50 minus TA times 1 divided by GIP. And what's the total angle of twist equal to in this case? 0, because it's fixed between those two walls. And so I can cancel these, multiply both sides by all that stuff, and we get negative 1.5 TA plus 50 is equal to 0. So TA so 50 divided by 1.5. So TA is 33.3 repeating. And then from the statics equation, they have to add up to 50. So 30, what? No, it comes out positive. And then 33.3 repeating plus torque B is equal to 50. So torque B is equal to 16.6 repeating Newton meters.